Hello guys, how are you? Give me just a minute. Reset with the app. And screen protection. Okay, good morning. Just resetting the screen with the whiteboard. I downloaded the software for the whiteboard, so it's now an app and not an online thing, and it obviously takes a little bit less. Got to get the size right. Okay. So, just a general announcement. You will notice some of you guys did attend last night's body doubling thing, which was nice. And some of you, not only did you attend, you got your goals done. So what I did last night was I shared a Word file. I think I'm going to do it in PowerPoint next time, but I shared a Word file, and you could type your goals in that Word file. I typed some goals in that Word file, and then we worked towards those goals. Many students asked questions, so I didn't quite get all of my goals done, but at least students asked questions, and we had some good discussions about organic chemistry with one of the students this morning. And those questions and what I showed him were good enough that I'm going to approach part of this lecture using that same technique, because it also shows you a good way to study and verify that you know what you're doing in this regard. So I am going to do that. I'm going to incorporate that into the lecture in just a few minutes. So thank you guys that attended last night. I appreciated the help in me getting what I was done, and I enjoyed interacting with you and appreciated the questions that you submitted. So, the course calendar for 114 does show a meeting online 8 to 10 a.m. That's the normal meeting time for this course. It's also in the, I think I put it in the calendar. Yep, it's in the calendar as an online meeting on the hybrid. So yes, it's on the calendar at 8 a.m. It's on the course calendar, and it's a standard scheduled course time. So, okay. So, just to reiterate, the scheduled meeting times for this course are Monday, 6:30 p.m. to oh, well, you may have set yourself up. This is Gen Chem 2, not Gen Chem 1, Zachary. So, for Gen Chem 2, we meet 6:30 to 8:30 p.m. on Monday and 8 to 11 a.m. on Wednesday. And this forms 4 hours of the 13 required hours per week for course. Now, the rest of the 9 hours should be readings, homework, and outside assignments. So, anyway, readings, homeworks, outside time. Let me turn the check-in on. I did forget to do that, set that up last night. So, I know in the past students have had trouble with actually meeting those goals. You are right. The board does not show. Thank you. And that's because it's looking for it differently. Why is it not showing? Oh. There it is. There you go. Yes, we are going to sign in for attendance. Just give me just a second on that. And this is lecture 4. I have just posted the attendance link in the live chat, and I'm pinning it to the top. And it is also going in the classwork. Attendance is up. So, back to what I was saying. So, New York State law, 13 hours per week for a 4-credit hour course. 4 hours of that is our required meetings based on Queens College schedule. The other 9 hours are readings, homeworks, outside assignments. You've got your readings, you've got your homework, and the 6 hours of optional body doubling work along / office hours is where I can help if you need motivation to put in that additional if you need motivation to put in that additional time, you've got somebody that'll help you in that regard. So that gives 10 hours, and that leaves 3 hours of independent time for study, homework, review. Now, again, that 6 hours is optional, and you are, if you are able to manage your own time, you can, of course, manage your own time. I mean, but know that this course is designed to kind of use that 13 hours that it's supposed to use for the full go. Now, the one thing I did want to ask you guys is, before we get started into formal lecture, is I do have and I got these specifically for students who might need something like this, and also for me. But I do have a variety of weekly planners and homework trackers and reading trackers and exam results and assignment trackers and study times and weekly plan forms. These are all digital. They can be printed. They could be uploaded into OneNote. They can, in other words, would these help you guys? Do you want me to make them available? Because I can upload them into Teams easily into a directory so that you have access to them to make them available for not just this course, but for any course you want to use them for. I just need to know if you actually want to use them. So there's even some Pomodoro planners and so forth. So let me know in the chat if you would like. Okay, that was fast enough. So while I'm here, so these are going to be, because I'm not going to link them because there's enough linked. So in general, shared, class materials, new folder, planner, pages. Ooh, what color? We'll make it that color. Ooh. So there you guys go. Now there's one other trick I want to show you in order to allow you to more quickly see the files that get posted in Teams. And I think you can do this, but I'm not sure. You can let me know. Now you're going to have OneDrive downloaded on your computer, but if you have that, you'll see a little sync button in this corner. And if you hit that, it's going to pop up and say they're syncing your files. And what that does is, at least in Windows, is if you have your file browser, it shows up under CUNY, and it will show the synced files. Now it's not through syncing them yet, but that's how it shows up. And if I hit class materials and hit sync, see, it shows up class materials, and that way I can you can see what's been added in a quick and clean way. So I did want to show you that and show you that that is available to you. Okay. So let us continue our discussion of nomenclature of alkanes. Oh, one other thing. I did post this as an announcement that there's now something I'm calling readings. So if you go to classwork and look in module 0, you will see now that there's a module 0 readings. And if you click on that PDF, you will see that I go through each of the chapters that is posted for OpenStax in module 0. I list the sections in the chapter and then the subsections in the chapter. Now the OpenStax book doesn't put numbers on the subsections, it just puts a heading, but lists automatically put numbers. And then what I did is I ranked those sections and subsections based on importance, with the ones listed as 1 being the most important sections for you to understand. So if you are reading the chapter, what are the sections you need to really understand, rewrite notes, spend some time with, and make sure you truly have this information? It's the ones in red. Now when we get to the non-review stuff, it does end at 9:55. I just put it at 10 because it's easier to write. And technically it ends at 9:50. So the class goes from 8 to 9:50. So anyway, the schedule is, since this is a review chapter, this is the material that you should go back and review, because this is straight from 113. Now, on chapter 21, this is what we are covering, because it's not review. This is stuff I don't, unless you had me for 113, you haven't seen this before. So this material is not review. Now we will finish this material today. But it is stuff that you haven't seen before. And this will be the review material, and this is what those CHEM activities are on. And then I'm going to provide some additional suggestions about how to study for exam and homework. But I did want to show that to you. Okay. Now, So, it's interesting, the app has different thicknesses. The easiest way to go about understanding and making sure that you can do organic nomenclature and so on and so forth is to practice. But how do you practice? So let's go ahead and get a little bit of vocabulary. So remember to check in before 8:45. So let us know. So for alkanes, these are saturated hydrocarbons. And alkenes and alkynes are unsaturated. Now, why? Because saturated and unsaturated are words that you guys hear. I mean, they're a big deal in diet, nutrition. Unsaturated fats, saturated fats. So what makes something saturated versus unsaturated? And to talk about that, I'm going to show the simplest of the alkenes. So this is a 2-carbon, so it's F, and it's an alkene, so it ends with ENE. So that's an unsaturated hydrocarbon. The other way we would draw this in chemistry is that, or you might, if somebody was being truly adventurous, they might actually draw the hydrogens on this. So all of these are general ways that we would write this. You'd also maybe see this written as H2C double bond CH2. So all of these are different ways of expressing the same compound. I don't want that to look like an equal sign, so I'm going to draw it kind of big. So all of these are different ways of expressing the same thing that you need to learn how to interpret and move between. Now, in all of these instances, I'm missing hydrogens in comparison to the alkanes. So the alkane version of this would be, oop, that's thick. Okay. Would be CH3, CH3, or C or that, or that. And again, that single line on a page, if you're a chemist, represents the other things I've got drawn. And this is 2 carbons, so F. It's an alkane, so ane. Now, if I look at the molecular formula here, I have CN, well, let me, C2H4, which in the general form is CnH2n. And the formula for the ethane is C2H6, so that has a general formula of CnH4n. 2n plus 2. So the difference between unsaturated and saturated is how many hydrogens do you have on the molecule. If your molecule has just single bonds in the carbons, and the maximum number of hydrogens you can have in a carbon-containing compound, i.e. it has no double or triple bonds with the carbons involved, then with just the carbons, and this doesn't count carbon-oxygen or bonds. This is mainly just the carbon-hydrogen and the carbon-carbon bonds. If it has no double or triple carbon-carbon bonds, then it is a saturated hydrocarbon. If it does have double and triple or triple bonds in the carbon-carbon bonds, then it's an unsaturated hydrocarbon. And that's a big deal in our bodies because our bodies have to approach double, triple bonds in breaking down carbon compounds that contain double, triple bonds differently than it approaches those of single bonds. So that's why that's such a big deal. Okay, so I wanted to go through that. And I also need to go through one other hint of vocabulary that gets used. Yeah, basically. So, saturated means you've got the maximum amount of hydrogens you could possibly have in the compound. Unsaturated means you don't. So it's about hydrogens. I remember when I was a student first learning chemistry, and at that time is the time when they were just coming out with saturated versus unsaturated oils and which one was healthier for you and which one wasn't, because keep in mind I am 50. And you know, I can remember thinking, what is it, why? And then it was like, oh, it's just maximum amount of hydrogen. Man, that's disappointing. Thought it would be something fancier than that. Yep, that'll work. It's a good way to remember it. Little mnemonics, I can't say that word, like that can help you remember. Share it with the class, because anything that can help remember vocabulary is a good thing. There's very few things you need to memorize. I will try to make sure to let you know what those things are. Saturate general world. So that's kind of one of those things you should know, just so that people can't fool you about what it is. Because that is in general press. And it is, people make a big deal out of that. And maybe necessarily you don't need to. So that's one of the things. The other thing is isomers. And we did see this in the last lecture. And I did, by the way, script, and we'll record a redo of that last lecture so that you have a streaming copy of it. So, but isomers, there's trying to, because I don't know. So there's what are called constitutional or structural. Isomers. And then there's optical isomers. And optical isomers have another oh, did I? Thank you for letting me know. I suspect that's because Teams is up. Can you hear me now? So can you hear me? Yeah, I just got warning that the my mic was being used somewhere other than here. Um, okay, so people can hear me again. Thank you. I got a little warning that my mic was iffy. So let me check and make sure. Yeah, I may have to reset it. Flip it, flip it. So can you hear me? Yes, okay, I'm back. Okay. Good to know. Let me know again if you lose me and I can flip on my OBS screen. So I don't know what caused that. Anyway, there's constitutional isomers or structural isomers. Those we tend to just call isomers. There's optical isomers. They have a fancy name. They are called enantiomers. Cis-trans isomers, you have to have an alkene. You have to have a double bond for cis-trans isomers. And we'll talk about that, but those would be constitutional isomers. Cis-trans isomerization is not an optical isomerization because it doesn't involve a chiral center. I do believe that we don't call those enantiomers. I will check. So this involves a chiral center. And chiral just is a fancy Greek word for mirror. So a chiral center allows you to have a mirror image. Now, when you're looking at your textbook and you're going through and you're reading your textbook and so on and so forth, any place where they talk about reactions of organic chemistry, we're not going to worry about reactions. So this is going to be focused on, so yes, cis-trans isomerization is geometric isomers or constitutional or structural isomers. So that's correct. Not all structures have mirror images. And we did go over this in class, but we're going to go over it again today. So, when we are given an alkane formula, and for this particular example, we're going to start simple and go and then go complex. So, C5H, 5 times 2 is 10, plus 2 is 12. So, this is a molecular formula. Now, how many isomers can we draw? So, this is how I go about doing this. And I'm going to draw them So I'm going to draw the same compound two different ways, side by side. Okay? So the first and most obvious version of this is CH3, CH2, 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 CH3. And that would be drawn 1, 2, 3, it's 4, 5. So those two are the same thing, and this is pentane. That's its name. Okay, now that's all I can do with that particular form because I have to have only 5 carbons. So in order to draw any other type of isomer, I have to shorten the primary chain. So now I'm going to draw a 4 chain, CH3, CH2, CH2, CH3, but I have one additional carbon because it's C5H12. So that means I'm going to have to put an additional carbon somewhere, and I can't put it here because if I put it there, I'd go back to the pentane, so I shall put it here. Now, the moment I add it, I have to get rid of that 2. 4 bonds to carbon. So I can only have 1 hydrogen there and keep my 4 bonds to carbon. So now I have this compound. Another way to draw that. 1, 2, 3, 4 is that. Now I need to name it. So my primary chain, I'm going to use the highlighter for that, is this. That's the one with the most carbons in it. And my numbering is 1, 2, 3, 4, or 1, 2, 3, 4. So that means in terms of numbering, I have 2 is lower than 3, and this is a methyl. So that means I have 2 methyl butane. Now, the next question is, can this have an optical isomer? Is there a mirror for this? Now, in order for something to have an optical isomer, I have to have 4 different things bonded to carbon. So on this carbon, I have 3 hydrogens and a carbon, so that's not an possible optical center. On this one, I have 2 hydrogens, a carbon, and, well, I have 2 hydrogens, a methyl group, and this group, which is technically an isopropyl group, but we're not learning that. So that's not an isomer. Methyl 2-butane, that the smaller things are what you're hanging off the longer chain. So methyl doesn't have 2 carbons. So methyl 2-butane would be saying, okay, I'm hanging a butane off of the second carbon in methyl, but methyl doesn't have a second carbon. The 2 in front of the methyl says I am hanging a methyl group off of the second carbon in butane. No, we're going to take a break here in 10 minutes. So, okay, so we have the methyl group hanging off of the butane, and it's in the second position. Now, I could also move and hang the methyl group here. And that would look like that. Now, same thing. Longest chain is that. Number the longest chain, 1, 2, 3, 4. 1, 2, 3, 4. The methyl group is shortest number is the 2, so this is also 2-methyl butane. In other words, these two are the same. They're not optical isomers, they're not structural isomers, they're the same compound. Exact same name, no chiral center. These are the exact same compound, they're just drawn differently. And that's the reason why you really need to be comfortable naming alkanes. Because if you name an alkane correctly, and then you have another drawing and you name it correctly and the names are the same, the compound's the same. And so you do need to be really careful with this. Because if you just saw these two, you'd say, oh, well, they're different. But they're not. They're the exact same compound. They're just drawn differently. So you do need to be very careful with that. So that means that is the only version of this I can draw that are the butanes. No, cannot be 2-ethyl propane. Because where would the longest chain be? There is no propyl chain in this. Well, okay, I can see that. The rules for organic nomenclature is you always find the longest chain. Always. Doesn't matter how the compound is drawn. So it doesn't matter if I were to draw this compound propane 2-ethyl. So there's your 2-ethyl propane, which is the incorrect name. So that would be, if I were to write it out without stick form, CH3CHCH3 CH2CH3. So the longest chain here is that chain. We number the longest chain 1, 2, 3, 4. So this is the incorrect name for 2-methyl butane. So while 2-ethyl propane will get you the correct structure, it's the incorrect organic name. So if you were trying to purchase it and you looked up 2-ethyl propane, you wouldn't be able to find that chemical to buy. If you look up 2-methyl butane, you can buy it. You can purchase it. So there is a set of codified rules for naming organic molecules. And those rules say we always start our name with the absolute longest chain possible that we can, longest continuous chain that we can draw. And then we build our names based on that longest chain. So if you're asking why that is, it's the rules. And I don't control those. IUPAC controls those, and I don't sit on the IUPAC committee. So they change the rules, by the way. About once every 10 years, they'll add rules or adapt rules or adjust rules. So, for instance, the transition between ferrous and iron 2 was a change in rules that IUPAC did. Oh, God, 20 years ago? I'd have to trace that. The change of standard pressure from 1 atmosphere to 1 bar, they did when I was a student. So the truth is only in the United States of America do we still use 1 atmosphere and talk about that being, quote, standard pressure in our textbooks, because it's not. It hasn't been for 40 years. 1 bar has been standard pressure in the scientific community for 40, 50 years now. So it's just one of those things that it's one of those things I don't particularly like about our freshman chemistry textbook, because it's actually only listed as standard pressure in some freshman chemistry textbooks, because when you go to the higher level chemistry, we've made the change. We know that 1 bar is standard. So okay, so one final thing before break. So we've done the only possible ones for that I can see for the butane list. So what about if I take 2? What if I go to propane? What are the only possible things I could draw with a propane base? We just said we can't hang an ethyl group off of a propane, but we can hang 2 methyl groups off of a propane and still get a C5. So we can hang the 2-ethyl propane one, which would be hanging an ethyl group off of a propane. That turns out to just be another way of drawing 2-methyl butane. So this is the only other way to hang 2 carbons off of a propane group. So this you would draw in stick form like that. And the name for this would be same type thing. We number. So 1, 2, 3. So we know it's a propane. We have a methyl group here. We have a methyl group here. And now both of those methyl groups are attached to the number 2 carbon. So it is 2, 2 dimethyl propane. So di here means 2 methyl groups. Both of those methyl groups are hanging off the second carbon. Now, how many isomers did we manage to draw? So I have this isomer, I have this isomer, and I have this isomer. So, looks like I have managed to draw 3 isomers of pentane. Now I'm going to Wikipedia that real quick. Just to see. No, 3 structural isomers of pentane. Yay! Okay. Yes, there is a longest chain. Admittedly, you could draw 2 different versions of the longest chain, but there still is technically a longest chain. So, doesn't matter which way I draw it, but once I identify which one I'm going to call the longest chain, so that's a longest chain. And then the methyl group comes off. The 2-2 represents where the methyls are. So this says I have two different methyl groups. This location of methyl groups. And when we go to a slightly, where I have a longer chain to play with, that'll become more apparent, because we can have a 2-3, we can have a 2-4, we can have a 2-5, or if I just hang a chlorine off. Oh my God. If you hang a halogen off of this compound, the number of isomers goes up dramatically. And that's what we're going to do after break. Okay, break. You guys can ask questions. We're on our 5-minute break. Yes, for that particular compound, the vertical could be called the longest, and you could name it off of the other one. And that's because both the vertical and the horizontal are both 3 carbons. So one of those could be named the longest. It doesn't matter which. Because keep in mind, in real life, in nature, this compound's tumbling and moving, and if it's a liquid or a gas, it's moving around all of the time, so it's not frozen in space. But as it moves, the bonding doesn't change. So for our next one, we are going to do but this is a good way to study and practice. Yes. So, we're going to do 2 more examples of naming hydrocarbons. I've already written the first one on the screen. You always order from smallest to largest. So it would be 2,5-dimethyl. There isn't a 2,5-dimethyl propane. It would be 2,2. Can't have a 5 because it's a propane. There aren't 5 carbons in the propane chain. In order to have a 2,5, I'd have to have hexane. I could have a 2,5-dimethyl hexane. Because there would be 5 carbons. But 2,5-dimethyl hexane would technically be an 8-carbon compound. So it would be an isomer of octane. And right now we're working on isomers of pentane. So the location of groups cannot have numbers larger than the number of carbons in your longest chain. And if you end up with something like that, it means you've probably not identified your longest chain correctly, which can happen. back to the question. Um, Structural isomers or constitutional isomers, basically that's where you start. So you draw constitutional isomers and then you check for the presence of chirality. If you have a constitutional isomer that has a chiral center, then it's going to have a mirror image that adds another isomer into the batch of isomers for a particular compound, and that other isomer is an enantiomer. And we'll probably see this with the example that we're about to do. Maybe. We may end up with a chiral center in one. Okay. So I've selected another compound. It's actually the same one we just did. All I did was I replaced a hydrogen with a chlorine. And so keep in mind, we only had 3 structural isomers, no enantiomers in the last one. Now let's see what happens with this one. How many structural isomers can we do? So we can start with our first one. So that 1, 2, 3, 4, 5. So that would be this, otherwise written as 1, 2, 3, 4. 1, 2, 3, 4, 5. That. So, since I do want to get you used to seeing this, 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, chlorine attached to the 5th carbon. That's how you draw that. So for naming, even though on habit we usually put the chlorine at the end, in terms of naming, the chlorine is what's considered a higher value add-on. So that means in terms of numbering, it starts from this end. And that's because chlorine is an addition to the alkane. So if I were to number it from the other end, 5 is higher than 1, so you don't use it. So this would be 1 chloro pentane. So the chlorine is in the number 1 position. You do the same thing for alcohols, which we'll do one in just a minute with that too. Okay, so the problem here is that's not the only place I could put the chlorine. I could put the chlorine there. Yep. So 1, 2, 3, 4, 5. I number it the other way. 1, 2, 3, 4, 5. Chiral isomers require having 4 different things attached to a carbon, and we haven't yet. Ooh, we just did that. We're about to be able to talk about that. Okay, so if I draw this way, 1, 2, 3, 4, 5, with a chlorine hanging off in that position. So chlorine's in the number 2 position. So this one going to put a dividing red line between these so that's easy to see where they break. Okay, so this one is 2-chloropentane. But notice this right here. So that particular carbon, if I focus on that particular carbon, I've got carbon, hydrogen, methyl, chlorine, CH2, CH2, CH3. But I could have also drawn this as carbon, hydrogen, chlorine, methyl, CH2, CH2, CH3. Now, that doesn't look like I made such a big deal about this. I mean, all I did was change that. Didn't change the name. The chlorine's still attached to the number 2 carbon. But it did change the structure. Now, in order to see that, I'm going to draw this in 3 dimensions. Okay? It's going to take me just a minute to get those done and paste them into this thing. You can put your chlorine on any atom. That's the point. That's why it's an isomer. Changes the name. It's a different named compound. Nope. The rule is if you're given a name, there's a rule. So, if you are told, you know, it's a 2-chloropentane, then the chlorine's got to be on the number 2 carbon. That's the rule. But if you're just told it's a chloropentane, then it can be any of these isomers. You got to have more information. And that's the point. That's why molecular formulas, while they're great for allowing you to calculate molecular weight, they do not tell you the structure of the compounds you're dealing with. So molecular formulas are not enough information. And that's why if you're a synthetic organic chemist and you are publishing a research paper, yeah, that's it for all chemicals. If you're publishing a research paper, you send your chemicals off to do mass spec and they send you back a molecular formula. You can't publish your paper just on that molecular formula. You have to provide a structure. You have to provide other evidence that that structure that you are providing is the correct structure. You have to do other types of spectroscopy, other types of measurements to show what the molecular structure is. So the molecular formula is just there as okay, they say they've got this structure, they have all this spectroscopy that shows that this is a structure, and their molecular formula matches. So that molecular formula is the least important thing. It's kind of the last cherry on top of a sundae. It's not the sundae. Okay, so what I've got open right now is a software that allows me to draw compounds. So there's methane, there's propane, there's butane, there's pentane, And then I can put the chlorine That's not what I want. Ah, there it is. You move over here and bond between you and you. Okay. So there's one particular structure, and no. So that's one structure. Control C, Control. Thank you. And now okay. So there's one structure. Now the other structure I need to do is I'm going to erase. Let me delete that. So to rotate this. So I want you to, I'm trying to get this where you can really see the structure. And then I want to select this, Control C, and I'm going to paste this in the whiteboard. Okay, so that's one. Yes, I know. Now, the other one is, I'm going to take this, delete it. I'm going to put the chlorine on this side. Computer's running slow. You. Come on. I don't care which one I use. Okay. So what I'm about to do is now I'm about to draw the bond from this side to this side. Hopefully it catches. Thank you. Okay. Now this one, okay. File. Okay. Now, let us swap this back over to whiteboard and get these put in the whiteboard. Okay, so there's the two that are now placed in the whiteboard where you can see that they really are different from each other in terms of their structure. So you can see here the hydrogens to the back of the page, here the hydrogens to the front of the page. Now, when you are numbering compounds, in order to tell one of these in terms of naming, these are both 2-chloropentanes. One of these is going to be called R chloro, sorry. R2-chloropentane. And the other one's going to be S2-chloropentane. Now, you don't have to know that. And you don't have to be able to, in this course, be able to identify which one of these is R and which one of these is S. And to be honest, I always struggled with it. Because in order to do that, you have to kind of rotate the hydrogen to the back and be able to visualize the rotation of the hydrogen to the back and be able to visualize how all of these other things change when you rotate that hydrogen to the back and then number it. And if the position is from highest position is clockwise, it's R, counterclockwise is S. Chlorine would be higher. So in terms of numbering, the numbering for this would be 1, 2, 3. The numbering for this would be 1, 2, 3. So I think, so you can see this kind of goes clockwise. So this is probably the R version. This one, 1, 2, 3, kind of goes counterclockwise. So this is the S version. But for this class, I don't expect you to be able to identify R and S. What I do expect you to be able to do is, yes, I got it right. This is the S. What I do expect you to do doesn't matter which one you swap. I could have swapped the hydrogens, or I could have swapped the methyls. All you got to do is swap 2. If you swap 2, when you have but that's a good question. I mean, don't get me wrong. Generally speaking, when you know you have a chiral center, in order to create the mirror image, just swap 2. And that's all you have to do. It was easy, and it was easier for me on this drawing to swap the chlorine and the methyl group, but you could easily just swap the chlorine and the hydrogen. So you just have to swap 2 in order to get the mirror image. And you can see that even by the naming. I swapped the 2 that I swapped to keep the hydrogen in the back to make it where I could actually identify the R and the S. But again, so this one is the S enantiomer. This is the R. But for this class, I'm not going through all those rules for the R and S. So you just need to be able to recognize this is chiral. And the reason for that is you have to count isomers. So technically, even though this is a single structural isomer, it actually is 2 isomers of the chloropentane, because this structural isomer has mirror images. So that's the structural isomer actually gives you 2 isomers, an R isomer and an S isomer. So it counts twice in terms of when you're counting isomers. You either have to do sticking into the page, that's why I've got it at the back, that's the back of the page. But I never did remember if it was a dash bond or a dotted bond. I'm teaching you guys basic naming, because at this stage for chemistry, I want you to begin to get used to naming these things. In enantiomers, you will go over it out the wazoo in the first chapter of organic chemistry. So for the general group of people here, if you can just identify, oh, that's a chiral center, and it's a 2-chloropentane, so there's an R and an S version, that's all you need to do for me. Okay? So I would mark this carbon with a little asterisk to indicate it's got a chiral center. And so it's going to have optical isomers. That's how you get back on that. Okay, so I could hang it there. Now, I could also hang it off of this one, and this would be 3-chloropentane, and that one's not chiral. And that's because if I look at this central carbon, I have a hydrogen and I have a chlorine, but I have 2 ethyl groups. Those are the same. So this carbon does not have 4 distinct different groups hanging off of it. So 3-chloropentane is not chiral. So far only 2-chloropentane is chiral. If I were to draw this with the stick model, 1, 2, 3, 4, 5, with the chlorine. Okay. Now, if I were to keep moving the chlorine over, if I were to move the chlorine over to this carbon, it's the same as up here, because when I number it, that's still a 2-chloropentane. And if I move it over to this one, that's 1 chloropentane. So I'm through with this particular version of hanging chlorines off. So now I've got to do what we did last time. And I now have to move to the butanes. So CH3, CH, hang a methyl group off of that. CH2, CH3. So that's kind of a starting point, and now I hang my chlorines off. So put a chlorine there. So this would be two chloro, 2 methyl butane. And it's not chiral, so I don't have to worry about that. This would be, now you do have to kind of prioritize chlorine higher in the alphabetical list. So this would be 2 chloro, 3 methyl butane, and here I do have a chiral center. Got 3 things hanging off of that chlorine. So in you guys, the way you can write this is I'm going to have an RS on that. That's just my way of denoting that. I also, no, I have 2 methyls hanging off of that one. So you put the chlorine off at the first one. I forgot that one. So this would be 1 chloro, 2 methyl butane, and here it's chiral, so there will be an RS on it. I can move that methyl so this would be 1 chloro, 3 methyl butane, it does if you use like fluorine, and if you have fluorine and chlorine, you have to pay attention to that. I'm not going to ever give you something that's got 2 halogens just because there's just way too many isomers. I might give you a name that was like 1 fluoro, 2 chloro, 3 methyl hexane and ask you to draw it, but what I'm not going to do is say draw all the isomers of something that's got 2 halogens. because there's just too many isomers. You'd spend an entire class period just drawing isomers. So this is a good question in terms of an exam question, because it does check to see, can you draw the isomers, can you find the isomers, can you find the chiral centers, and can you correctly name everything you draw. So it's an amazing question for an exam question. But I mean, there's a lot of isomers, and we're we've got a lot more to draw. So well, actually not that many more, but still there are a lot of isomers. But you can see that it's relying on the still marking the longest chain. And that's why, if you're looking at here, you'll notice I didn't hang a chlorine off of this. And that's because if I hang a chlorine off of this, I'm still attached to the longest chain. 1, 2, 3, 4 with a chlorine. So this would just still be 1-chloro-2-methyl butane. So when you are drawing structural isomers, the trick to knowing, do I have a new structural isomer or did I just draw what I've already got drawn, is you name it. And you name it correctly. You don't name it the way you think it should be named. You sit down, you count the number of carbons, you find the longest chain again, and you name it. You go through all of the naming steps and you name it. And then if you've already got that name, then it's the same isomer. You just drew it differently. And that's one of the things that causes issues when students first start organic chemistry, especially if they haven't already been introduced to this concept. So what's the hardest thing in chapter 1 of organic chemistry? And the hardest thing on the first exam is the fact that I can draw these compounds in all sorts of different ways, and it's the same bloody compound. So what usually gets students in trouble is the fact that you can draw a compound like this or like this. Let me get so I can draw this or I can draw this, and your brain, I mean, we're very visual people. When you first look at that, you go, those are different. But they're not. These are the exact same compound. They're just drawn differently on the page. So that's what gets students in trouble in organic chemistry. And that's part of the reason why I do take the time to go over organic nomenclature in, I go over it in Gen Chem 1 and then again in Gen Chem 2. And I do that because when you've seen it twice already, when you see it that third time, it makes sense. And you can kind of settle into it. And then that also means that when you do hit organic, instead of worrying about naming and isomers and all of that jazz, you're focused on how it reacts. So it reduces the amount of stuff you have to memorize. It kind of front loads that. Now, I think in terms of importance, it goes down the periodic table. So fluorine's more important than chlorine, is more important than bromine, is more important than iodine. In other words, I think electronegativity is what determines the importance. And then for the carbon groups, what determines it is the largest number of carbons. So ethyl's more important than methyl in terms of what's hanging off. So if you're numbering, if you can number the ethyl group to a lower number, that's what you do. So, in other words, if you have a choice between two ethyl, no, you wouldn't have a 2-ethyl group. 3-ethyl. You can have a 3-ethyl group. So 3-ethyl 4-methyl or 3-methyl 4-ethyl, you're going to name it 3. ethyl for methyl, just because the ethyl group is more important in terms of orienting your numbers. Now, you just saw me stop and do something, and I'll talk about that while we're on break, because I don't want to write it down. So, sorry. So we're at break. You cannot have a methyl in the number 1 position, because that just basically increased the length of your longest chain. You can't really have an ethyl in the number 2 position, because that basically increases the length of your longest chain, because 2-ethyl is the same as a 3-methyl with a longer chain compound. So basically, the position of your group, the number for your group, like the number in front of your branched group, has to be larger than the number of carbons in your group. So if you're just doing pure alkanes, now it's different if you've got, no, it's not different if you have a chlorine hanging off. So again, longest chain is your starting point, and you cannot have an alkane hanging off of something that is going to make your chain longer. So that means a 2-ethyl is technically just making your chain longer. So generally speaking, if you're going to have an ethyl group hanging off of your compound, it's got to be in the number 3 position or higher. If I'm going to have a methyl group hanging off of my compound, it's got to be in the number 2 position or higher. If I'm going to have a propyl group hanging off of my compound, it's got to be in the number 4 position or higher, which means I've already got to have, what, a really long chain carbon. I can't be playing with, 5 carbon atoms, because there's no way I can put a propyl group hanging off of that with only 5 carbons to begin with. So this is all things that help you check yourself. If all of a sudden you're looking at that going, wait a minute, I have a 2-ethyl? That doesn't make any sense. And then you can go back and check and see if you misnamed. So other questions? But yes, Yanni, one of the things you learned, one of the things you have to kind of memorize for organic chemistry, but not for me, is the importance of different elements, like is fluorine more important than oxygen in naming, and so on and so forth. But generally speaking, if it's got an oxygen in it, it's got another special name, because it's either an ester or an ether or a carbonyl or a ketone or an aldehyde, so you're not necessarily as worried about it, or an alcohol. So you don't really have to worry about oxygens and nitrogens and sulfurs and phosphoruses, because they have their own nomenclature. They're all different. In other words, they're all different. They're not alkanes. It's only the halogens that can hang off of an alkane and still use alkane nomenclature. Okay, so let us continue this real quick. Okay. So 1-chloro methyl. Can't hang the methyl off the 5 position. So 3, 2, 1-chloro, 2-chloro. So I do have 3-chloro. Oh, I have the 2, 2. I do. I don't have the 3, 3. Okay. So now I'm going to start drawing these where I can draw them a little faster. 1, 2, 3, 4. That's actually no easier to draw, to be honest. So CH3, CH2. No, that's the same. Now, I was thinking, okay, I need to do the 3. So CL, CH3, CH3. But if I look at this, because the chlorine and the methyl group aren't separated, if I number this correctly, this is 2-chloro, 2-methyl, butane, and I've already got this one, so technically this is not new, already drawn. Let me put that in a different color. So, nothing new there. I've hung the chlorine off of there. I've got the methyl as far as I can. So I think I've done all of those. So that leaves me then the final one, which is I'm now starting with this as my base. And I need to hang a chlorine off of it. So this would be 1-chloro, 2,2-dimethyl propane. Now, this also does have a chiral center. No, it does not have a chiral center. 3 methyls hanging off, that does not have a chiral center. Now, if I were to draw, it's a really good one for this. If I were to draw C, Cl, CH3, that 1, 2, 3, 4. Okay, that's fine. And name it, same thing. This is 1-chloro, 2,2-dimethyl propane. So same compound. And just as you guys noticed the last time, if I were to draw this this is still 1-chloro, 2,2-dimethyl propane. So I only get one isomer for that, for the propane. All 3 of those are just different ways of drawing the same thing. So This counts as 1. So there's 1 isomer. That's not new. This one did not have so that's 2, 3, 4. That counts as 2. So this is 3 and 4. Because of the chirality. This is 5 and 6. This is 7. This is 8. This is 9 and 10 and 11. So 11 isomers instead of 3, all because we added a chlorine to the initial alkane. So you can see now why organic chemistry has its own branch and its own 2-semester sequence. Small things, like I just added a chlorine to an alkane, and all of a sudden I went from having 3 different isomers, 3 different compounds that have the same molecular formula, to having 11 different compounds that have the same molecular formula. So the richness and variety of carbon bonding is amazing, but it also leads to an incredible complexity in the nature of things. So we are at the end of today's talk, and we've gotten through most of what I wanted to cover. So the final things that we will cover really briefly in the lecture on Monday before we do homework, and this will not be part of your homework, will be nomenclature of benzene rings and how you do this for alcohols. So if instead of a chlorine group, if I hang an alcohol off of here, how does the nomenclature change? The numbering doesn't change, but how you write it changes. So I'm going to set that up down here on this very last one, because we've got it drawn. So if I were going to do this, if it were an alcohol instead of the chlorine. So CH3C, and I'm going to do the CH3s here. CH2OH. If I had that, so instead of a chlorine, I'm hanging the OH off. This would be 2,2-dimethyl propane 1-ol. That's how you would name that. So this is what indicates where the alcohol is. So it's a little strange. I agree. That's a little strange, but that's how they did it. It used to be you would name this 2,2, the older version of this, methyl 1-propanol. But they decided to move this 1 where it reflects that it's the alcohol that's in the 1 position. So this is older nomenclature. And when I say older, I'm like, 20 years older. So the correct IUPAC name, this is the correct IUPAC name. So we'll do some examples of that using what we've already got on Monday before homework, and I'll briefly go over how to name benzene compounds because those pop up in the lab pretty quickly, and they're really, really easy to name. And the rest of the nomenclature we will leave for organic chemistry. So basically, I want you to be able to recognize functional groups. I want you to be able to name simple alkyl alkanes, branched alkanes. I want you to be able to recognize if there's a chiral center, but you don't have to name that yet. You don't have to pick is it the R or the S version. And I'll want you to be able to name simple single alcohols, not diols. Diols have 2 alcohol groups. We're not going there. So that's what you'll be expected to be able to do by the first exam. Other than that, it's 9:50, so I'll entertain last questions, and we are through for this particular meeting. There will be another body doubling work along tomorrow night if you want to work on homework. And I will be posting some suggested homework problems from the organic chapter on picking functional groups and on naming. So there will be that. It's the chloro's not 2 because it's still hanging in a 1 position. So you always number from the lowest number. So for the red one, the main chain would be here because that puts chloro. The homework that I post on organic nomenclature, some of that will be might be asked on Monday. Yes, because we've just spent 3 lectures on organic nomenclature. But it's going to be something like this. So if you want to practice for the organic nomenclature, just write an alkane down, any alkane that's under C10, and ask yourself, can I draw all the isomers? And can I name all the isomers? And if I add a chlorine or a fluorine or a bromine or an iodine, 1. Don't add 2. Good God, don't add 2. I can add 1 chlorine, bromine, iodine. Most of your homework has been posted for a while. It's in ClassWorks. Module 0. Suggested homework 1, homework 1, homework 1, homework 1, homework 1, homework 1, homework 1. It's all there. What I'm telling you is another type of homework that is directly related to the lectures. And that is, write down an alkane, C10 or less. Draw all the isomers and name them. Add a halogen to that alkane. Draw all the isomers and name them. And can you find if it's got a chiral center? That's a homework. And it's really good practice. So homework will always be uploaded to under general, shared, class materials. It's always going to be in there. For some reason it's not. Thank you. You see suggested homework, it's always going to be uploaded there. And then when I get a chance, I will link it into Classworks. One chloro, 2 methylbutyl. Sorry. 1 chloro, 2 methylbutyl. Okay. So, why does this have a chiral center? So if I look at this, I'm going to use green. There's a methyl group. If I look at this carbon and I just circle the groups around it, are those groups different? Are all three of them distinctly different from each other? So, 4 different groups. Oh, yeah, you can't. Sorry. So, 4 different groups attached to the carbon implies chiral. So while chirality is a big deal chemically, it's a really simple thing to see. All you have to do is look at your carbon. If it has 4 different things attached to it, it's chiral. It really is that straightforward. And that's why things with double bonds can't be chiral, because you only have 3 things attached to carbon. So it has to be a sp3 carbon. It has to have only 4 bonds to it for chirality. I know sometimes it's like, oh my god, it's got to be such a complicated concept, but because, you know, we make a big deal out of it. And from a chemical perspective and from a body's perspective, it is a huge deal. Our body, almost a ton of the biochemicals in our body are chiral. And a ton of the pharmaceuticals we put in our body are chiral, and they really matter. So being able to recognize chirality is really important, and yet it's really just having 4 different things attached to a carbon that are different. They have to be distinctly different. So it's actually a little bit, I don't know if it's amazing or unnerving that our biochemistry and our biology, our molecular biology is so sensitive to the fact that you can have 4 different things attached to carbon and it matters. Because like prion disease, like mad cow disease, what causes a misshape in the folding of the protein can be something as simple as the chiral center changing from R to S during a replication. So it's a really important, chirality in our body is incredibly important, and yet it's just having 4 different things attached to carbon. It's like I said, I don't know whether to find that astonishing, amazing, or terrifying. I really don't. But it's something. It's certainly something. So other questions in this regard? Good question. seeing no other questions, I'm going to end the broadcast. I shall see you guys on Monday in person. And that we'll start from there. But I am going to have my office computer set up to do to record the broadcasts for the future as well.